Okay, so we almost still have the 10 minutes. We have another exercise, and we can try to also practice how can we apply the Bernoulli equation to predict the flow velocity. So this exercise is a different material. We are located. We are in the wind tunnel. So that means the material of the fluid is the gas and the air gas. So I just highlight. We also put the pitot tube, and we actually know the pressure difference is equal to the 730 par, and this is why we directly understand the delta P, because we put the pitot tube. Okay, so what's the questions? What is the air velocity in the tunnel we have? So, and I write down the government equation here, so you know that's very simple. We already know the delta P is the 730 par, but we didn't know the density of the air, right? So let's just take a look at what the parameter you have. So you understand the exercise provide the absolute pressures here. So you have the absolute pressures, and you know that the temperatures. And I also provide you the gas constant. So you may know what the equation we can apply is the ideal gas law, right? So that's based on the ideal gas law, we actually know that the absolute pressure will equal to the rho RT. And we don't know the density, but the other parameter we actually know. So the rho you can rewrite is equal to the absolute pressure divided the gas constant and the absolute temperatures. So I just put the number inside here is 98 kilo absolute Pascal, and the gas constant is the 287 joule over kilogram Kelvin. And the absolute temperature, we know that the 20 degree in our environment. So there is 293 Kelvin. Okay, so you can use your calculator to double check the density of the air under these conditions. So for me, I use the calculator to check, and divided the 293. It's quite close to the 1.2, but we need to, the answer here is 1.1 around the 7 and the kilogram and the meter cubic. Okay, so we have the air fluid density. So we put back to the equation, the V is equal to the root of the 2 times delta P is 730. The Pascal is Newton per meter square, and divided the 1.17 kilogram and the meter cubic. Okay, so you can check the answer. The 2 times the 730 divided the 1.17. Okay, so and take the root. It's around the 35.4 the meter per second. Okay, so it's almost the final exercise. We are trying to apply the Bernoulli equation to compute the flow velocity in different environment. So this is a final exercise. Our environment is the wind tunnels. So the previous we put the meters into the pipe flow. Okay, so a different condition you have a different measurements to understand how effect of the flow velocity. Okay, so just continue this idea. In next semester, in our laboratory experiment, we will run the experiment we call that the Bernoulli testings. Okay, so again, you can see there is our device, but we already buy the new ones. So next semester, you don't operate the experiment based on this device because we already buy the new ones. But the idea is the same. We have the pipe here, and as you can see, the pipe here, this is a pitot. This is a pitot tube. Okay, you can see the pitot tube here, and there is the pressure recorder. So you have the pressure recorder here, and we call that the recorder. So what are the meanings I call that the recorder? Because you can understand the delta P based on these recorders. Because you put the tube inside the nozzle. So as you can see, we have the nozzle here. This is our nozzle, 束缩管. Okay. So in the nozzle, you have a different cross-section line with a different cross-section length. And when you adjust the pitot tube locations, you will measure the different pressure changes. And you can, based on the equation showing here, you should understand based on the pressure difference, so you can compute a different velocity at a different location. Okay, so that's the Bernoulli testing. You just based on the device to measure the pressure difference and put into the equation, and then you can know how the velocity field, flow velocity in the field. And the right hand side, you didn't, I have not teach before. So this will teach in the chapter 5. We call that the continuity equations. So right hand side, we can also compute the theoretically flow velocity based on the continuity equation. But you can understand what are the meanings because we know that the different cross-section area, we will have a different velocity. But they are equal. So velocity 1 multiplied cross-section area 1 will equal to the velocity 2 multiply the cross-section area 2. They are always equal to the constant values. Okay, and we call that the continuity equation. So two equations, we can compute the two different velocity at the same point. So this experiment, we will compare the velocity computed from different equations, and to discuss the reason why they look the difference and what are the major reasons to explain the discrepancies between the two velocities. Okay, so it's a very good experiment in next semester. You will try, and this is before our Kahoot. I wondering to introduce a little bit about the rotational flow. So before that, all the conditions we consider the flow is no viscous effect. But in real case, it's not really true for all the cases. So sometimes the important thing is we wondering to characterize the rotational motions of the flowing fluid. And sometimes we say that the rotations. If we say, okay, there is some rotational in our flow field, and that indicates the viscous effect will be involved in your problems. So in that case, if your flow is start to rotate, that indicates the viscosity effect is important. So we cannot always say the flow is inviscid flow. That indicates when the rotational happens in the flow field, and the viscosity effect should be taken into account in our problem. we cannot neglect the viscous effect. Okay, so that's a major problems. What kind of flow is rotational flow, and how can we define the flow is rotational or not? So that means if the flow not rotate, we can call that is the non-rotational flow. So we need to provide the certain definition to determine the flow is rotational or not. That's why we need to do some calculations and we can understand. Okay, so that's the slide. We consider the Coulter flow. As you remember, the Coulter flow we are discussed in the chapter 2 when we introduce the viscous equations and we introduce the Coulter flow. So what's the Coulter flow? The Coulter flow indicates we have the velocity point here, and this direction is the y directions. And we have the different velocity speed with a different magnitude. And this flow direction, we call that the u directions. So you can figure out what's the slope in here. So the red line in here is the velocity gradient. Sometimes we use the du, dy, right? And we know that the u velocity will be changed with the y locations, but it is always equal to the constant value. So we have the constant gradient of the velocity. And if you base on the viscosity equation, we know that the shear stress will equal to the viscosity dynamic multiply the du, dy, right? So if your velocity gradient always the constant value, that indicates your shear stress. You have the shear stress also the constant, right? Okay, so that's the viscosity equation tells us the physical meanings. Okay, so but for this Coulter flow, we can identify some rotational angle changes with a different time. As you can see, this is for the T1 time, this is for the T2 time, and we pick out the point, and we do some measurements of the angle theta. As you can see, the theta angle here are different at a different time. That indicates the flow is rotational flow, especially for a Coulter flow. And how change it for a theta? As you can see, the dashed line here, this is a dashed line. We call that the bisector. Bisector is indicates the 中分线. And then the bisectors with the angle between the horizontal line. So how can we measure the theta angle? Is you have the horizontal line along the straight line, and the angle between the bisector and the horizontal line, we call that the theta angle. So if you see the theta angle will be changed, that indicates that the flow is rotational flow. So how can we quantify and define the flow is rotational flow? We need to measure the theta angle first. And we identify the theta angle at a different time points. And then we can say, okay, the theta angle will be changed with a different time point. And we call that the rotational flow. Okay, a little bit complicated. And the next week, I will teach you how can we compute the theta angle. Okay, so maybe today I stop here and we are move to the Kahoot and highlight the quiz, and we have the quiz today.